Hi, and welcome to the Foundations course lesson 5 on estimating and testing for differences. While the previous lessons focused more on theoretical concepts, we're going to delve into the practical stuff today. We're going to start with how to assess normality, how to construct a 95% confidence interval, and then I'm going to show you how to use the GCR Statistics test wizard and how to test for differences in continuous as well as categorical data. This lesson comes with a small warning because it contains many mathematical formulas, but don't focus on them too much. Instead, try to grasp the underlying concepts that they represent. Statistical software will do these calculations for you. We're going to start this lesson by looking at how to assess for normality. Because if we want to test for differences, we need to know whether our data are normally distributed. And you can either use a statistical test itself to do that, or a graphical assessment. I wouldn't recommend using statistical tests because they are not sensitive enough in small samples and too sensitive in large samples. I would recommend using a graphical assessment. And for most tests, an approximate normal distribution is sufficient because these tests are relatively robust. Here's an example of a perfect normal distribution, where in the histogram you can see a nice symmetrical bell curve, and the box plot shows you symmetrical whiskers that are equally long, and the median right in the middle of the box. Here's an example of a variable that is not normally distributed, where in the histogram you can see that the median is more to the left side of the graph, but a lot of data still extend towards the right side. So the range goes further to the right than to the left. And you can also see that here in the box plot, where the whisker on the right side is longer than on the left side, and the median is located further to the left in the box. So that means that most of the data will be found around this area, but there's still some data on the right side of the graph. And that means that this variable is right skewed, or in other words, positively skewed. And this is the other example where data are left skewed, where you see the exact opposite, where most of the data are found on the right side of the graph, but a lot of data still extend towards the left side. So the range on this side is longer, and the median sits on the right side of the box, but the left whisker is longer than the right one. And oftentimes you can change the skewness of data because we know, for example, from a lot of laboratory values like the white blood cell count, that they tend to be right skewed. But if you take the logarithmic transformation of that value, they also often become normally distributed, like this, where when we take the log of the white blood cell count instead of the white blood cell count, we get a nice symmetrical bell curve. All right, moving on to 95% confidence intervals. When we construct a 95% confidence interval, we usually do it for either a single sample mean or proportion, or a between group difference in means and proportions. And that 95% confidence interval gives us an idea about how well our estimate is approximating the population value. So let's say we draw a random sample of patients where we measure systolic blood pressure and we derive a mean of 120 and a standard deviation of 15. But how does that actually relate to the population mean? Well, this story is probably familiar by now, but we measure our parameters in the sample. We have an N is 50 patients, and our sample mean is 120, our standard deviation is 15, and then we calculate the standard error, where we assume that the sample standard deviation is a good proxy for the population standard deviation, and we divide 15 by the square root of 50, which gives us a standard error of 2.12. And that standard error is the standard deviation of multiple sample means, but you can think of it as a measure of the uncertainty with which we estimate the population measure with our sample. And this is how you construct a 95% confidence interval. You take the sample mean and you subtract from that sample mean 1.96 times the standard error. And that gives you the lower boundary of the 95% confidence interval. Whereas the upper boundary is formed by the sample mean plus 1.96 times the standard error. And that 196 is the critical Z value for the probability 0.025 in the standard normal distribution. The story about the tails on the left and the right side being the 2.5% on each side. So if we add them up, we get 5%, and 100 minus 5 is the 95 that we're looking at. In our example, this is how we would calculate the 95% confidence interval. So we take the mean of 120, and then we subtract 1.96 times 2.12, and that gives us a lower boundary of 116, and the upper boundary is 120 plus 196 times 2.12, the standard error, gives us an upper boundary of 124. So our mean with the 95% confidence interval is 120, and then 116 to 124 for the 95% confidence interval. But what does that mean? It means if one would calculate the 95% confidence interval repeatedly, so over multiple random samples, 95% of them will contain the true population mean. So this again is a very theoretical concept because we're not going to repeat our study multiple times. It's just that the intervals depict likely values for the population value. So in our example, we have calculated a mean in our sample of 120, but it would not be odd to have a population value that ranges from 160 to 124. This figure displays the concept of the 95% confidence interval graphically, where repeated studies show different sample means and 95% confidence intervals. And the true population mean value here is depicted with a dotted line. And you can see that there's considerable between study variability in terms of the means and the 95% confidence intervals. And actually, some of the sample means are lower and some of the sample means are higher than the true population mean. But what's clearly visible is that almost all of the studies contain the true population value within the 95% confidence interval boundaries. And to be more precise, 19 out of the 20 studies do contain that value in their confidence interval. But one study, the black one over here, doesn't. And the problem with performing a study and looking at a 95% confidence interval is that we don't know which one of these studies we are. So that's the reason why we cannot say that we're 95% sure that the confidence interval that we have constructed contains the true population value. We can only say that to the best of our ability, we consider it a range for likely estimates of the true population value. But we should acknowledge that sometimes the population estimate may incidentally fall outside that interval. We can extend this confidence interval principle to other levels of confidence, like the 90% confidence interval or the 99% confidence interval, just by simply switching the critical Z value to corresponding probabilities of 10%, so 5% on each of the tills, and 1%, 0.05% on both till ends. And for a 90% confidence interval, you would use a Z value of 0.164 instead of 1.96. And for a 99% confidence interval, you would use a value of 2.58 instead of 1.96. Here's a word of caution on small samples. We know from the central limit theorem that sample means will be normally distributed regardless of the underlying distribution. However, in small samples, and especially in those with less than 30 to 60 patients, it is questionable whether we can approximate the population standard deviation with the sample standard deviation. And using the normal distribution approach with the Z value may give too narrow confidence intervals. So there's an alternative approach where we use the t-distribution instead. And that will give wider confidence intervals in small samples, but equivalent confidence intervals in larger samples. So we can actually always use the t-distribution if we want to. And the formula is quite similar to that of the Z-value approach, but the difference is that we don't have one fixed critical value for the 95% confidence interval. And in the Z-value approach, we used 1.96, but in the t-distribution approach, we use a critical value that depends on the number of observations in our study minus 1, which is the degrees of freedom for the t-distribution. And we have this guy, the guy who worked for Guinness, to thank for it. So I'm going to show you how the GCR Statistics test wizard works. And this is a representation of the choices that you can make in the GCR Statistics test wizard. I'll just click on the link, and then it will open the gcrstatistics.com website. And on this test wizard, which is here underneath the button Research Tools. And it's just a click button system where you can choose whether you want to evaluate differences or associations. And let's say we want to evaluate differences between groups or variables. And we're dealing with continuous outcomes. And we can choose the amount of groups that we want to compare. Let's say we want to compare 2 groups. And we say they are not related or independent. Then the GCR Statistics test wizard will come up with the test that we need to use. So for normally distributed outcomes, we should use a 2-sample students t-test. And for non-normally distributed outcomes, we should use the Wilcoxon-Rank sum test or Mann-Whitney-Hughes test. And then if you want to make another choice, you can just click on this button to go up to the starting screen again. So that's the test wizard. All right, let's resume our lesson. We are going to look at how to test for differences in continuous data now. The general structure of a test for differences in means is depicted by its test statistic in the form of a difference in mean divided by its standard error. So if you have a relatively large between group mean difference in relation to its standard error, you will obtain a relatively large test statistic. And large test statistics have a low chance probability, so they will result in small p-values. The 95% confidence interval is just simply the difference in means minus and plus a critical value times its standard error. There is an interesting relationship between the 95% confidence interval and statistical tests. Let's look at the example where we want to compare the means of 2 different groups. We are going to calculate a test statistic with the general formula difference in means divided by its standard error. And we do that under a specified statistical model where we are going to assume the null hypothesis of no difference. And the alternative hypothesis is that there is a difference. And we usually use a two-tailed test, so that means we don't really care which of the group means turns out to be the larger one. And then there are other assumptions that we have discussed before that are also included in the specified statistical model on how we performed the study, collected the data, and analyzed them. And eventually we get a p-value, which is the probability of obtaining a difference as found in the study, or even more extreme, under the assumptions in the specified statistical model. And that p-value, unfortunately, is receiving a wrong interpretation by many scientists. They think that if the p-value is lower than the pre-specified alpha level, then that proves a difference, because the alpha level is the false positive rate that we accept in a study. So if we accept that 5% of the times we are going to claim that we have found a difference, whereas in reality there is no such difference, and the p-value eventually turns out to be lower than that alpha value, then there must be a difference. And on the other hand, researchers also often claim that if the p-value is equal to or larger than the alpha level, then that proves no difference or equality of the group means. And this is a problem called the bright line thinking, because researchers want to have an easy solution to a p-value, and they want to use just two different categories. But we should actually interpret the p-value meaning differently. If we have a small p-value, then that tells us that our data are incompatible with the specified statistical model. And that means that either there is no difference, or there is a difference between the groups, but one of the other assumptions is violated in the specified statistical model. And if the p-value is large, then that only means that the data are not unusual under the specified statistical model, but there might still be a difference in group means. Now we can also look at the 95% confidence interval. And we do that by calculating the observed difference in mean between the groups, and then presenting the 95% confidence interval with its lower and upper boundary. And that 95% confidence interval shows us a range of likely values for the group mean difference. And that's interesting because it doesn't only contain the estimate in our study, but it also shows you a range of other values that might as well be likely. And if that interval does not contain 0, so the range falls below 0 or above 0, then that's not a likely value under the assumptions that are made of in the specified statistical model. So in that situation, we are confident in the difference found. And so we actually derive a lot of information from a 95% confidence interval that is also supplied by the p-value. And that is because they share a lot of things, among which the difference in means that we have found, the standard error, and a certain statistical distribution, like the t-distribution or z-distribution, chi-square distribution, etc. So to recap, the p-value is informative, but it shouldn't be used as a binary category. Instead, it should be used as a continuous measure that gives us a sense of how compatible our data are with the specified statistical model. And we should instead focus on the observed difference in mean with its 95% confidence interval, because it gives us a range of likely values for the difference, and it also shows us how large that difference is. And that has real clinical applications. And one more thing to add is that the larger our study, the smaller the standard error will be, and thus the narrower the range of the confidence interval boundaries. And so we can be more certain about our prediction of likely values for the observed difference. And this thinking also applies to relative risk measures like the risk ratio, odds ratio, or hazard ratio. But instead of focusing on the value 0 for there is no difference in the null hypothesis and the 95% confidence interval, we need to focus on the value 1, because if, for example, the risk ratio is 1, then that means that the risk in both groups is equal, or in other words, there is no difference. Now let's look at how to perform these comparative tests in practice. We're starting with the comparison of two independent group means with a normal distribution. The GCRstatistics.com test wizard tells us that we can either use a z-test or a two-sample students t-test. And this is how we do that. We're going to start with the z-statistics method. First, we're going to look at the difference in mean between both groups. And then we are going to calculate its associated standard error, which is the square root of this term, and that term is the variance of group 1 divided by the number of patients in group 1 plus the variance in group 2 divided by the number of patients in group 2. And if we use that standard error term in the formula for the 95% confidence interval, along with a critical value of 1.96, we can construct that confidence interval by just looking at the difference in mean minus 1.96 times the standard error, and then the difference in mean plus 196 times the standard error. Of course, because we're using a z-statistic method, the critical z value is 1.96. But we don't often use this method because we've learned that almost all of the time we can also use a t-distribution. So we can use a t-statistics method instead. But if we do that, we also use the difference in mean, but we need to use a pooled standard deviation to calculate the standard error. And that pooled standard deviation is a little complicated if you write it down, but you can just fill in this formula to get it. And then we use a critical t-value, but that critical value is variable and it depends on the degrees of freedom. So usually the degrees of freedom are the number of patients in group 1 and the number of patients in group 2 minus 2. And then we can fill in the 95% confidence interval. We take the mean, the group mean difference, and then subtract the critical t-value, which we can look up in the table at the number of degrees of freedom that are applicable to this situation, times the standard error, and then we do the same for the upper boundary plus this term. And the formula for the t-value is just simply the difference in mean divided by the standard error as calculated here. So with that t-value, we can look up the p-value in a t-table by choosing either a one or two-tailed test, the t-statistic value, and the total number of patients minus 2 degrees of freedom. Or we can let a computer calculate it, because modern statistical software packages will easily give you the results of a student's t-test. And the larger the t-statistic, the smaller the p-value. But there are certain test assumptions that should be met, among which is the independency of the groups, approximately normal distribution, so slight deviations from normality are okay, but the distribution should certainly not be skewed, and the group variances should be approximately equal. We can also test whether a sample mean is different from a known population mean. And for that, we use an one sample student's t-test. And here we calculate the difference in mean by subtracting the population mean value minus the sample mean value. And the standard error is the standard deviation of the sample divided by the square root over n. And then if we have a large group, we can use the Z statistic, where we just use this difference in mean between population mean and the sample mean to calculate the 95% confidence interval. But we can also use a t-statistic approach where we have to look up the critical t-value for our sample size. And the t-statistic is the difference in means divided by the standard error with n-1 degrees of freedom. And the same applies here. We can look up the p-value in a t-table, or we can let the computer calculate it, and the larger the t-statistic, the smaller the p-value. And only normality of the distribution is a test assumption. All right, now what if the groups are dependent or clustered, and we want to compare means between those groups? Well, in this situation, we use a paired student's t-test. So first, what we're going to do is we create a new variable where we subtract the value of group 1 or time moment 1 from the second group or time moment 2. And then we have a new variable that depicts the difference between both, and use the one sample approach to construct a 95% confidence interval and t-test. So this is what it looks like. We first take the sum of the values before minus after, and then divide it by the number of pairs to create a new sample mean of the difference. And then we calculate the standard error as the standard deviation of the sample divided by the square root over n. And we take the t-statistic approach to construct a 95% confidence interval. And the t-paired statistic will be the sample mean of the difference values divided by the standard error with n-1 degrees of freedom. And it's exactly the same as with the one sample approach, where we can look up the p-value in a t-table, and we only have normality of the data distribution as one of the test assumptions. You can compare the means of more than two independent groups by one-way ANOVA, and ANOVA stands for Analysis of Variance. It's important to note that if the between-group variability is much larger than the within-group variability, then that signifies an important difference of the group values. And as a measure of variability, we like to use variance. So we can calculate the between-group variance and the within-group variance. Remember this formula from lesson 1? And that's exactly what we do in the ANOVA. It's a little bit complicated, and you're not going to do this by hand, probably. You can just let the computer do the hard work for you, but this is how you calculate an ANOVA. We start with the sum of squares between groups with its associated degrees of freedom. Note that k here is the number of groups. And then we calculate the mean square between groups by dividing the sum of squares through its degrees of freedom. And then we calculate the sum of squares within groups with its associated degrees of freedom. And next we calculate the mean squares for the within group component. And finally, we divide the between group mean square by the within group mean square. And that gives us an F value, and that's the test statistic value for the ANOVA. So we can look up the p-value in an F table by choosing a one or two-tailed test, the F statistic, and k minus 1 and n minus k degrees of freedom. Or of course we can let the computer do the hard work. And also here applies the larger the F statistic, the smaller the p-value, because that means we have a large between group variance compared to the within group variance. And it's assumed that the data are normally distributed and the group variances are approximately equal. A little bit more about the ANOVA. The one-way ANOVA test for two groups is actually equal to an independent student's t-test. So it doesn't really matter which one we use. And we can test for differences in group means for more than two groups. But if we obtain a significant test result, it only tells us that there is a difference between any of the groups, but not in which comparison. So to determine that, we have to look at the estimates of the mean and the standard deviation, as well as its associated 95% confidence interval, to determine which groups differ from each other. What do we actually do when some of our test assumptions are not met? For example, when comparing means and the groups are not independent. Well, if they're paired, then we use a paired t-test. And if the group standard deviations are not equal, then we can either try to transform the variables, for example with a logarithmic transformation, or use a non-parametric rank-based test, or less commonly use an alternative test like the Fisher-Barons or Welch test, or estimate the difference between the means and construct a 95% confidence interval of the difference using something more complicated like the bootstrap method. And when normality assumptions are not met and transformation of variables does not help, usually the way to go is to use a non-parametric alternative to the standard tests, which are rank-based, so by order of magnitude of the observations, and are based on comparisons of medians instead of means between the groups. So we're not going to discuss non-parametric tests in detail because the calculations are pretty complicated, but I'm just going to briefly show you which tests to use in which situations. Now, if you want to compare one group with a population value in a non-normally distributed data, you should use the sign test. And if you want to compare two independent groups with non-normally distributed data, you use the Wilcoxon rank sum test, and another name for this test is the Mann-Whitney-U test, and that's the non-parametric variant of the two sample students t-test. If you want to compare two dependent groups with non-normally distributed data, you should use the Wilcoxon signed rank test, and that name is pretty similar to the former one, and I remember the difference is in the D within the signed rank test, which stands for dependent groups, and that's the non-parametric variant of the paired students t-test. You can also compare more than two independent groups where you have non-normally distributed data, and then you use the Kruskal-Wallis test, which is the non-parametric variant of the one-way ANOVA. Now that we've discussed how to determine differences in continuous data, we're going to look at categorical data. And in categorical data, we're usually interested in comparing the proportions of a certain outcome in at least two different groups. And we can depict that very nicely in a 2x2 contingency table, where we show the results for a positive and negative outcome in different columns, And then for group 1 and group 2, and sometimes this is called the exposed and unexposed group, or experimental group and control group, in different rows. And then we get letters like this: A, B, C, and D. And if we want to compare the proportion of patients with a positive outcome in both groups, we divide A with A plus B. So we look at the number of patients with a positive outcome as a ratio of the total number of patients in group 1. And then we do the same for group 2, and we compare those proportions. But we can also look at the negative outcome proportion in a similar way by comparing the ratio of B over A plus B and D over C plus D. So here's an example of a placebo randomized controlled trial where we look at the 1-year survival and compare that between patients being treated with an experimental drug and a placebo. And the first thing we want to know is what is the absolute risk of death, or in other words, negative survival after 1 year. So to determine that, we look at the number of patients in this cell, which is 200 patients died after 1 year after being treated with the experimental drug. And we had 1,000 patients in that group, so the absolute risk is 200 divided by 1,000 is 20%. Whereas in the placebo group, it's 700 divided by 1,000, it's 70%. So you're much more likely to die after 1 year after having gotten the placebo. But how much more likely? Well, we can express that in either an absolute sense or a relative sense. The absolute risk reduction is 70% minus 20%, which is 50% in total. So that difference is expressed in percentage points, and it's an absolute risk reduction or difference. But we can also express it in a relative risk sense, where we divide 20% with 70%, and that gives us a relative risk of 30%, if you round it up, or 29% to be more exact. And that means that if you are treated with the experimental drug, you have 30% the risk of dying at 1 year in comparison to the risk after being treated with a placebo. Another interesting number to calculate is the number needed to treat, and that is calculated by dividing 1 with the absolute risk reduction, and in this case it will be 1 divided by 0.50, and that results in a number needed to treat of 2. And that means that we need to treat at least 2 patients to prevent 1 death after 1 year. We can actually calculate all these different risk measures, such as the absolute risk reduction, relative risk, odds ratio, and number needed to treat, on the basis of the following formulas. And there's something I want to point out, that the group 1 is usually the experimental group, so the absolute risk in that group becomes the experimental event rate. Whereas group 2 is usually the control group, and the absolute risk in that group is called the control event rate. So the absolute risk reduction is the control event rate minus the experimental event rate, whereas the relative risk is the experimental event rate divided by the control event rate. Now the odds ratio is a little bit different, because up to now we have calculated proportions on the basis of probability. But in odds, we look at the ratio between event and non-event. So the positive odds in group 1 is A divided by B, whereas the positive odds in group 2 is C divided by D. And the odds ratio is simply the ratio of the positive odds in group 1 over the positive odds in group 2. And you may interpret the odds ratio as something that's pretty similar to the relative risk, although they may be very different, and we'll come back to when that situation occurs later in this course. And the odds ratio is often found in calculations based on logistic regression analyses. And the number needed to treat, we already saw, is 1 divided by the absolute risk reduction. In essence, we're doing the same thing in categorical data research as in continuous research. We take a random sample, and in that sample we estimate a probability of an event, but we want to know how that relates to the true underlying population value that is unknown to us. And so we calculate the standard error. In this case, we multiply the probability of an event with that of a non-event, and then divide that by the total number of observations and take the square root of it. In this example, where we studied 100 patients, we observed 20 events, and so 80 non-events. We estimate the probability of an event as 20%, and our standard error will be 0.04. Note that this approach is only applicable if we have at least 10 events and non-events. And that has to do with the fact that we are substituting the population proportion value with the sample proportion estimate. And notice that this standard error formula is pretty similar to the one in continuous data research, where we use the sample standard deviation, but here we take the product of the probability of an event and the probability of a non-event. And also, our way of calculating a 95% confidence interval for proportion is pretty similar to that of a mean, but instead of the sample mean, we use the sample proportion here, and then subtract 1.96 times the standard error and add 1.96 times the standard error. In our former example, this would result in a risk estimate of 20% and a 95% confidence interval ranging from 12% to 28%. And that just simply tells us that it would not be unusual to expect that the true population risk would be in the range from 12 to 28%. We can also test whether a sample proportion estimate is different from a known population value. And we can do that with the z-test, a binomial test, or a chi-squared goodness of fit test. And this is how we do it. We use the standard error formula that I've just shown you, as well as the 95% confidence interval construction. And the z-test is the sample proportion minus the known population proportion value divided by the standard error, and that will give you a z statistic. And again, with that z statistic value, you can simply look up the p-value in a z table or let the computer calculate it. And the larger the z statistic value, the smaller the p-value that you will find. But you need to meet these test assumptions of at least 10 events and non-events, as well as a approximately normal distribution. More commonly, we want to know whether the proportions in two independent groups with a normal distribution differ from each other. And we can either use a z-test or a chi-square test to determine that. This is how you do it for a z-statistic method. But we need to know that we have at least 10 events and non-events, or a total number of 40 patients in our study. And then we calculate the difference in proportion between both groups and construct a 95% confidence interval based on that difference. The z-statistic is simply the difference in proportions divided by the standard error. And the standard error is calculated by the product between the probability of an event and the probability of a non-event divided by the total number of patients in the study, and then take the square root of that. Instead of focusing on the difference in proportion, We can also use the risk ratio. And to do that, we calculate something that's called the error factor with this mathematical formula. And the standard of the log risk ratio here is calculated as follows. And the D's stand for the number of events or deceased in group 1 and 2 respectively. And the N's stand for the number of patients in group 1 and 2 respectively. And when we've calculated that, we can determine the 95% confidence interval by dividing the risk ratio with the error factor to get the lower boundary and taking the product of both those terms to create the upper boundary of the 95% confidence interval. And the Z statistic is the log risk ratio divided by the standard error of the log risk ratio. And we can actually do exactly the same for the odds ratio. More commonly, people will use the chi-square test to determine whether there are significant differences in event proportions between two groups instead of using the Z statistic approach. And at the heart of this test is the difference between expected and observed outcomes in the 2x2 contingency table. We should realize that if there is no difference between both groups, we would expect an equal proportion of events and non-events in both groups. But it's questionable whether we actually observe that. And here I have depicted how to calculate the expected values in the 2x2 contingency table. Note that we replace outcome plus or event with D for diseased patients and outcome minus with H for healthy patients. And then we can calculate the proportion of diseased patients in this study by taking the ratio of D over N, and the proportion of healthy patients in the study by taking the ratio of H over N. And then we can simply multiply it by the number of patients in group 1 for the diseased proportion and the healthy proportion, and the number of patients in group 2 for the diseased proportion and the healthy proportion to get the expected values in all these cells. And the next step is to compare the values that we would expect in each cell with the observed value. To get the chi-square test statistic value, we first focus on each cell. And in each cell, we determine this term, where we subtract the expected value from the observed value and take the square of it and divide it over the expected value. And after that, we take the sum of all these cells' values to get the chi-square test statistic. And this is distributed with n-1 degrees of freedom. Another way of rewriting this formula is with the following equation. And with that chi-square test statistic value, we can look up the p-value in a chi-square table, or we can let the computer calculate it for us. The larger the test statistic value, the smaller the p-value. And what's interesting to note is that the chi-square value is equal to the z value squared, so we will always get the same p-value with both of these approaches. But we need to fulfill the test assumptions of at least 40 patients in our study, or 20 patients in the study, with an expected count in all cells of the 2x2 contingency table of at least 5. And if that's not the case, we should use another test that's called the Fisher's exact test, which is more of an exact approach of calculating the p-value by calculating 2 times the probability of the observed 2x2 table plus the probability of an even more extreme outcome. We can also test for differences in more than 2 groups with regard to their proportion if these groups are independent and show a normal distribution. And for that, we also use the chi-square test. But here we just extend the number of rows in the 2x2 contingency table, and we talk about R by C table where R stands for the number of rows and C the number of columns. And here we have depicted a 3x2 table. And again, we look at the expected versus observed values, and we use the exact same approach as for the 2x2 contingency table. The only difference here is that we use a different number of degrees of freedom, which is determined by the number of rows minus 1 times the number of columns minus 1. We can even look at differences in proportions of events between two or more groups that are not independent but dependent. And for that we use either the Z-test or the McNemar test. And in these tests we're looking at a matched pair analysis where we compare two different variables with each other that either have a positive or negative outcome. And so you can have discordant or concordant pairs. And this discordant pair is called R, whereas this discordant pair is called S. And if there really is no difference between both variables in the paired analysis, we would expect approximately half of the discordances here in this cell at R and here in this cell at S. And so with the Z-value method, we calculate a 95% confidence interval like this, and we can determine the Z-value with the following formula. But we can also use the McNemar's test to determine a chi-squared test statistic for paired analyses with the following formula. And with these formulas, we can again look up the p-value in a chi-squared table or let the computer do the hard work for us. And just remember that we need to fulfill the test assumption here that the number of discordant pairs in R plus S should exceed 10. Well, wasn't that a long lesson on estimating and testing for differences? You're a tough nut to crack. Great job hanging in there, and get ready for describing and testing relationships.